So we're here to present this Vertica Spark connector. We have this implementation, and we will talk about the implementation and approaches. Our implementation has been given to several customers for preview and feedback. We will make this public fairly soon. So this connector enables both data and computation. We enable data move from Vertica to Spark, and Spark come back to Vertica. We also enable the computation pushdown for Spark, from Spark to Vertica. We also will talk about the data locality optimization, computation pushdown, and also the data movement from Spark to Vertica. So Vertica is an analytics platform that supports advanced SQL analytics, and it's a share-nothing MPP database. The data are stored in column-oriented storage. Vertica supports standard SQL interface and support very fast query. It also supports many analytics capability that is built into Vertica. And Vertica also supports user to extend Vertica functionality with user-defined functions.
So as such, we think that Vertica is an ideal data source for Spark because you can connect those capabilities that Ray just mentioned to Spark's workflow.
Right. Vertica, so in the above, this is a Spark execution pipeline, and in below, this is a Vertica execution pipeline. Our connector will connect these two parts of an execution pipeline, and the result data of Vertica execution pipeline will be fed into the Spark execution pipeline. So in this way, we can connect these two parts of an execution pipeline into a single one. And we also enable, in this way, we also enable the computation or push down into Vertica. So this connected pipeline connect computation pipelines of Vertica and Spark in an optimized way. The data, first, the data are transferred in parallel channels. And Spark and Vertica can leverage the data locality optimization, leverage the data locality information in Vertica. And this connector also enables the computation or push down into Vertica. For example, the Spark SQL will support filtering, projections, joins, and aggregation. Those are the candidates that can be pushed down into Vertica. So in Vertica, a table is hash segmented. So in this example, table T are hash segmented by ID. So segmented means partition, so it's hash partitioned. And each segment will be stored in one Vertica node. So in this example, the different color represent different node and different segments of the data. If one tuple, after applying the hash function, located in between one segment, it will be stored in the corresponding Vertica node. So our connector will enable a Spark locality-aware partition. So each Spark locality-aware partition will use Vertica data distribution information to generate a locality-aware query. So to generate such query, the Spark partition need to understand the upper bound and lower bound of the segments, and also the segmentation expression.
So as you can see here, this particular example here with the ring shows 4 segments. That corresponds to 4 Vertica nodes. And we also have 8 of these purple circular arcs, and each of those represents a Spark partition. So each of those Spark partitions, 8 of them, will generate a query that kind of looks like what we show in the bottom left corner here. The key component is what is there in the where clause. The where clause basically states that that query only wants the data from that range of data on this hash ring. So there is a lower bound and an upper bound. Because the hash expression is on the ID column, we simply say that that query wants only the data where the tuples have the hash values between 0 and, in this case, 278,985. And the other partitions will similarly have their own ranges. Each one will have a different range. So each partition will try to get a different piece of the data. Together, they will cover the entire hash ring and be able to get all of the data. Now, one key thing that you want to notice is that in this particular example, the Spark partitions all respect the segmentation boundaries in that there's no Spark partition will ask for any data that is not on the node that it connects to.
So in this page, we will talk about the locality-aware query. We will comparing the non-locality-aware query and the locality-aware query.
So in general, because Vertica is a shared nothing distributed database, a client can connect to any Vertica node, and any Vertica node can serve a query. So the node to which a client connects is called the initiator node. So the initiator node is responsible for taking that query. And since it's a distributed database, that data that is needed to respond to a said query can be on all of the nodes and all of the cluster. So generally what happens is the initiator will form a query plan, what we call a query plan, which will then be broadcast to all of the nodes. All of the nodes then are responsible for executing this plan and returning some part of the data which fits the requirements. Now, however, in our particular case, we're generating locality-aware queries. And that means that this kind of thing is actually unnecessary.
Yeah. In the non-locality-aware query, the query actually sent to Vertica initiator, and the initiator will distribute this query plan to all Vertica nodes. And this distributed plan will be executed on all Vertica nodes, and the data will be returned from this distributed plan to this initiator, and the final result will be sent back from this initiator. In the locality-aware query, because the query only requests the data reside on one node, which is the initiator node, the query will be sent to this initiator, and the query plan will only retrieve the data from the initiator. But note that all the distributed query plans still need to be sent to all nodes and still need to be executed there, even there's no data to return.
Now, the scheme that we talked about in the last slide, like I said, involves all the nodes processing a particular query plan. Now, in this case, we have locality-aware queries. So even though we are able to eliminate the data shuffling inside a Vertica cluster because of our predicate, the where clause, it's still going to send this query plan to all of the nodes, which means that the other nodes that don't have any of this data will still have to do some kind of processing, and that's unnecessary. So we can approve upon that by using a feature we call query pruning.
Yeah, we introduced this query pruning to reduce the unnecessary query plan distribution and unnecessary CPU and other resource utilization. So we can prune the unnecessary execution plan running on those running on those nodes that doesn't have any data request. So as we can see, with this pruning, the query will only be run on the initiator node, and that is a node that has all data on it. So we also support defining arbitrary number of Spark partitions over arbitrary number of segments. In this example, we can see we have a set of 4 segments, which is a hash partition of Vertica table. And over these 4 segments, we can define 2 Spark partition or 3 Spark partition. So we also support Spark partitions over unsegmented table replicas. So in this case, for unsegmented Vertica table, the data are replicated onto multiple Vertica nodes. And in this case, the connector will generate a synthetic Spark partition. Each partition will only retrieve one of the subrange of the data. In this case, the data are replicated forth from replicate 0 to replicate 3. And there's 4 Spark partitions are defined. Each one only retrieve one subrange of the data from one of the replica. So here is the performance characteristic of our connector. As we can see, for 4 Spark partitions and 32 Spark partitions, at the beginning, there's a CPU bulge, and then CPU utilization keep low as the rest of the time. After applying this is without the query pruning. After applying the query pruning, this high CPU utilization period will also disappear. And for the network throughput, we can see when we use 4 Spark partitions, the Spark job cannot generate sufficient workload to load the data, so the network throughput is not fully utilized. When we use 32 Spark partitions, the network throughput is fully utilized to transfer data from Vertica to Spark. So as you can see, there's an optimal number for partitions and optimal parallelism to use to load data from Vertica to Spark. So here we show the scalability of throughput. So the loading time increase proportionally to the size of the data. When we have an 80 gig data site, the loading time is around 300 seconds. When we have a 560 gig data, the loading time is around 2,500 seconds. So this experiment is done on a 1 gigabit network, 4 nodes Vertica cluster, and 6 nodes Spark cluster. Since we already talked about the locality-aware query, now we will talk about how to use this query to generate computation pushdown. We already implement the pushdown of filters, projections, constar, and we are working on pushdown of joins and aggregation. In the future, we will consider pushdown the user-defined functions. So pushdown means move this computation from Spark side to Vertica. So there's several schemes for pushdown. For those per tuple computation like filtering and projections, we will always push down this computation from Spark to Vertica, possibly to reduce the amount of data need to move from Vertica to Spark. And for join and aggregation, we can do locality-aware pushdown. That means when the join keys and aggregation keys are co-segmented inside Vertica, we can do this locality-aware pushdown. If this co-segmented does not exist, we can run a single query in Vertica to run this join and aggregation.
Now, the same trick that we showed earlier with the locality-aware queries can be applied to pushdown operations like for joins as well. But with the special requirement, of course, that these 2 tables have to be segmented on the same column, and the column has to also be the segmentation key. If we satisfy this requirement, then we know that the same values of the join column for both of these tables will be on the same node in Vertica. If we have this information, then we know that if we do partial joins at each of the Vertica nodes, then we can essentially have a result that is equivalent to a full join. So see here, this example, if you're joining tables A and B on column foo, then we can translate that into the same kind of join statement on each node. And each node will receive a query where we have this same hash boundary check, which means that you only want the particular join result from that node with data on that node. Note that this same trick can be applied to aggregations as well if the aggregation key is also your segmentation key.
So this is the performance impact of pushdown. As we can see, if we don't push down the computation, the data transfer time and the loading time for 8 gig data is around 300 seconds. Then we can apply this pushdown. We can apply projection and filtering separately, or we can combine them, push down them together. Then the loading time are dramatically reduced because the amount of data need to be moved is reduced dramatically. So Vertica have many built-in functionality that will be a good complement to Spark. So Vertica support geospatial analytics, semantic analysis, sessionization of event streams, time serial pattern matching, and many more. So user can combine these two systems and enrich their Spark side filtering, feature engineering, and so on.
So far we've talked about Vertica to Spark data, which is data that flows in one direction, where Vertica is your data source. And we realized that there is also a use case for the other direction, where Vertica is an endpoint rather than a data source. And when that is the particular context, Spark is usually used as something like an ETL engine. And so we've investigated a couple of approaches for this direction as well. And the primary objective of both of those approaches is that we want reliable and fast bulk loading of data. So these two approaches, we're going to be calling them direct and indirect. The direct approach is direct in the sense that you only have these two systems, Spark and Vertica. We will open parallel channels, again, from Spark to write into Vertica using parallel tasks in Spark. That seems like it might be a superior solution, but as we will see, there are several complexities and nuances involved in that. Secondly, we have a two-stage approach, or the indirect approach, which involves a third system. In this case, this example is HDFS. That will be used as an intermediate storage that Spark writes to, and then Vertica can then read from HDFS. So you might be wondering, why don't we just use Spark JDBC writer? So Spark, yes, by default does have a JDBC writer. You can hook that up to any storage system that has a JDBC driver. But as we see here, there is a lot that we can gain in terms of performance. It actually doesn't do everything that efficiently. For example, in this case, we were able to load 10,000 rows in 6 seconds, whereas in our experiment using the default writer, it took 525. Another tricky thing that we have to deal with when we use a parallel direct approach is the issue of duplication. So the Spark engine is smart enough such that if a particular task fails, it can restart it. So let's see what can happen, right? So you have lots of Spark tasks that are writing into Vertica in parallel. If one of them fails, Spark can restart the task. And in this case, this is not a good thing because we want to avoid duplication. Now, as far as we know, not only does the default writer have not so good performance, it also doesn't do this kind of check. So what is the big picture of our direct approach? The direct approach basically involves a bunch of intermediate tables inside of Vertica directly, which we use as durable storage. These tables allow the Spark tasks to coordinate themselves. And there are basically two stages, right? The first one is where the Spark partitions all write into a staging table. And after that, there's another stage where the Spark tasks do this thing called leader election. out of which only one task will emerge as being the one that commits the result into the final target table. So again, let's revisit this kind of a picture where you see lots of Spark tasks running in parallel. Now we have this red arrow, which we think of as a duplicated task, which Spark can do if you're in a speculative execution mode. Or this particular example can also sort of represent the restarted task case. But it's relevant to both scenarios. So if these two things belonging to the same partition are going at the same time, and they both write to a staging table, we have to be able to roll back the duplicate. The way we do that is we tell each Spark task to update this task status table, and to set the status, done equals true, where the task equals its own task ID. Now in this case, since there are two of these tasks and this operation is atomic, only one of them will be able to succeed. So in this case, if the black arrow, since it got there a little bit sooner, will get a result of 1, and it'll commit the result that it wrote to the staging table. In the other case, the red task will get a result of 0, and it has to roll back what it did. And finally, after the data all go into the staging table, you need to elect one task to be the final committer. So again, here, assume that you have two tasks in close contention. They're running together, but they're very close to each other. In terms of execution, they're almost synchronized. After they write to the staging table, they go to the status table. And after that, they'll have to check this table called the last committer table. Only one of these tasks is going to succeed. Why? Because again, they'll do something like update last committer and set my ID equals set ID equals my ID, where ID equals -1, because the value is initialized to -1. So the first guy that gets there will be successful, and he'll see that he's the committer, and the other guy will fail, and he'll simply terminate. Now note that after this value is updated, the last committer will always have the task ID of the one that was successful. So even if that task fails later on, once it gets to this point, it can read from this table and see that the ID stored in this table matches its own ID, and then be able to proceed. Likewise, the other tasks will read this table and see that it is not the last committer, and then just stop. So after we've elected the leader, we basically have to move the staging table to the target table. And we do that simply by either renaming the table into the target table or doing an append if it's in append mode. So that's very simple. So okay, so this is the direct approach. What are the pros and cons? Of course, a pro is that you don't have to have an external system beyond Vertica and Spark. But it does have an additional bit of complexity in that you have to coordinate these tasks properly such that you get exactly one semantics. Now, the two-stage approach is a little bit simpler, so I don't have to spend as much time on it. So let's say you have intermediate storage like HDFS. All you have to do is write to HDFS, let's say using orc. And then from that, we have a very optimized orc reader that we can invoke on the Vertica side. And we can say copy to target table from HDFS using orc. Now, and that will tell Vertica to read from HDFS and store the data into its own table. Now, why might this be a better approach? Well, it allows us to use Vertica's built-in copy command, right? So it does natively have this copy function. And as such, it allows Vertica to do its own resource control. And in that case, it might have better scalability, as opposed to the direct approach where you have lots of direct copy commands. There's a lot of parallel queries into Vertica, which might overwhelm the cluster. This also allows us to use the optimized orc reader that we have, which we developed in collaboration with Hortonworks, which I've been told it has been tested and is robust and is good. And of course, it's simpler code logic because we only tell Vertica once to copy the data from HDFS. Of course, there are some cons as well because it means that we do need to have an additional write stage to HDFS. And it also requires the dependency on this other system. OK, so in conclusion, we've talked about a connector that can move data from Vertica to Spark and also from Spark to Vertica. The V2S side, it integrates well with Spark SQL's data source API, which means that a lot of the things that you do in Spark SQL, like aggregations, joins, filters, projections, these can all be pushed down into the queries that we generate. And so Vertica can process all of that computation. And when it processes that computation, it reduces the data transfer from Vertica to Spark. We utilize this hash range queries to minimize intra-Vertica data movement because each query only asks for local data. And of course, we also talked about this node pruning feature that we have, which allows Vertica to prune out the query plans that are unneeded for the rest of the Vertica nodes. Now, from the Spark to Vertica side, we talked about two approaches. One is the direct connector approach, which efficiently and reliably coordinates transfer with parallel Spark tasks. And also, we've talked about a different approach, which involves two stages, using the native copy command and our orc parser. So, if you're interested in Vertica, we encourage you to give it a try. There's a community edition that is free, and you can download it, up to 1 terabyte and 3 nodes. And the material that we covered in today's presentation, we don't have anything public as of yet, but if you're really interested, please visit that link and register. Someone will be in touch. Thank you very much.
OK, so we have time for a couple questions. So yeah, go for it.
So in the Vertica to Spark, how do you avoid multiple scan of the partition when you have more tasks on the Spark side, more than the number of segments on the Vertica side? So if I have like a 20 Spark tasks reading 10 Vertica partitions, now you're going to end up having every partition read twice, right?
So yes, you're correct. So let's see, do we have this slide here? OK, well, in the example that we showed, we had actually something similar to that, right? We had four Vertica nodes and 8 Spark partitions, right? So even with this node pruning trick that we talked about, those two queries that go to one node, yes, there will be a little bit of extra work because the full scan has to happen for each of those 2 queries. But at least with the node pruning, it doesn't have to also take care of the other requests on the other nodes. Yeah.
Do you try to run Spark with equal number of tasks as the number of partitions, or you keep that?
No, actually, experimentally, we found that we can have a lot more Spark partitions than Vertica segments, and it's actually we get better performance that way. So more parallelism.
Yeah, the parallelism is try to optimize the network throughput for data transfer. And you can use cache in the Spark side to avoid some rescan if possible.